We're going to talk about biodiversity, species loss, and bioengineering. So far in the course, we've mostly been motivated not just by learning about living matter and bioengineering, but the applications and primarily people health or medicine. Truly a profound area that motivates bioengineering, learning, and practice. It turns out, though, the molecules of life, they don't really care what the use is. Maybe if we got good at bioengineering proteins, we could make medicines not only for people, but the planet. So let's think about the health of the planet, what we call planet health. And one, as we'll learn, dimension of planet health is how is the rest of life on Earth beyond Homo sapiens doing? So that's what this set of slides is about. Let's get going. For example, here's a creature commonly known as the horseshoe crab. You can find these in the Atlantic Ocean, parts of the Pacific Ocean, elsewhere on Earth. This species is thought to not have changed very much for almost 500 million years. It's, quote, older than the dinosaurs. And shows up on the beaches every now and then. Such an interesting creature. In nature, living things are related to one another, the web of life. And so here we see a horseshoe crab in relation to the red knots, a bird that migrates. If you look at the world map down below in the bottom right, this bird is migrating, and oftentimes it'll stop and feed on what's available, including things related to the horseshoe crab. So that's a relationship between species. Well, let's ask a more personal question. What's the relationship between our species, Homo sapiens, and Limulus polyphemus, the horseshoe crab? Here's a photograph from the early 20th century in Delaware Bay, Pennsylvania, New Jersey, that part of the eastern seaboard of the United States. And you can see that the fellas here are stacking up lots and lots and lots and lots and lots and lots and lots of horseshoe crabs, and then taking them away on trolley carts or train cars. It looks like they're using this for fertilizer, right? So you could do farming. What's this going to do to the horseshoe crab? It's going to reduce the population of horseshoe crabs. Now, to make this story more interesting, I have to introduce something related to people health. It turns out that planet health and people health are going to be connected. So even if you care about medicine, health, and only people, you end up needing to care about nature. So check this out. There's in human medicine an issue where you get a fever, and one type of fever is derived from a pyrogen, and pyrogen, something that generates pyro, a pyromania, pyrogen, a fever-causing agent. A type of pyrogen, one type is an endotoxin, which is part of a bacteria. And so if you get a bacterial infection, you might get a fever, in part because you might have endotoxins or pyrogens. In medicine, not only is that an issue, but if we use bioengineering to make medicines, then we might want to make sure we're purifying our medicines from any endotoxins. Or if we have something that is being made to be injected into people, it could even just be a syringe with a needle, or it could be a saline solution. We want to make sure that there's no endotoxins in those things either, right? Because if there's an endotoxin, then a person might be very sensitive to that, get a fever or worse. All right, so just on background, there's endotoxins. Some endotoxins are derived from certain types of bacteria, and so we have to make sure anything we're using in medicine, doesn't have an endotoxin associated with it. Well, what's this got to do with the horseshoe crab? All right, thanks for your patience. We want to make sure the things that we're putting into people in medicine don't have pyrogens or endotoxins. It used to be that the way you'd figure this out is you'd take a little bit of your injectable, and not all of it, right? And you'd test it on rabbits. And so you'd have these poor rabbits in a situation like this, and you'd give them an injection of what you wanted to see, whether it had an endotoxin or not. And if the rabbit got a fever or worse, you're like, oh, no, that's not safe to put in humans. It's called the rabbit pyrogen test. Right? You still haven't gotten back to the horseshoe crab. Well, this fella, Jack Levin, in the 1960s, was studying the blood of horseshoe crabs And horseshoe crabs, they have to worry about infections too. And so it turns out they don't have a human immune system. They have their own sort of way of dealing with microbial infections, obviously, and it has to do with something in their blood. And within their blood, they have the capacity to aggregate or coagulate around anything that might be a bacteria or related to bacteria, like an endotoxin. And Jack and colleagues figured out that if you extracted this factor found in horseshoe crab blood, instead of taking a sample of your vaccine or saline solution and injecting it into rabbits, you could just mix it up with this horseshoe crab blood extract and see whether or not you got this coagulation or observable property. And so this becomes known as the limulus test. Limulus for the horseshoe crab, and a test, a way of determining whether or not IV fluids or pacemakers or injectable drugs have endotoxins in them. All right, so anything going into a human patient needs to be tested to make sure it doesn't have endotoxins, and we're going to use horseshoe crab blood to do this test, the limulus test. Well, where's the horseshoe crab blood come from? Remember that photograph of fertilizers? It's coming from the horseshoe crabs. And so, for example, there are harvesting facilities. This one is in South Carolina, where you can see the horseshoe crabs. They've been captured through fishing or harvesting from the ocean. And some of their blood is being removed. Their blood's blue again. I guess blood that's red has iron in it, but blue is going to have copper in it. That's pretty cool. And the horseshoe crabs are still alive. They have some of their blood drained. It's collected in these bottles, and you just see the statistics. 500,000 animals collected a year. Don't take all their blood because they die. Take a third to a half. This blood is worth $60,000 a gallon, like 10,000 times more valuable than milk. And how would you do if somebody took a third of your blood, or you lost a third of your blood? You might die, right? And so not all the animals survive this process. There's a significant mortality rate. This is also that we have medicines that are safe to inject. What's the impact of this on the population of horseshoe crabs? It's threatening their existence. So on the right, you can see a little schematic, and it's got this interesting notation in the bottom. What's the conservation status of the species, the Atlantic Ocean horseshoe crab? The further to the right on the scale it is, the less worried we are about this organism going extinct. All the way to the left, the organism is extinct. What does extinct mean? It's not found alive on planet Earth anymore. Like the passenger pigeon went extinct, the dodo went extinct, the dinosaurs went extinct. That's what's on the left. And so anything moving towards the left is at risk of being increasingly threatened, vulnerable, becoming extinct. And so this one looks like it's not too bad, but it's threatened, right? And it's, the more we're using medicines, the more we're going to have to collect horseshoe crabs to get their blood. And so it's probably trending to the left. Here's another way of looking at that, conservation status, right? So if we just go back to the horseshoe crab again, it's VU, or vulnerable, right? And so, it's like heading towards extinction. I'm using the example of the horseshoe crabs. It's just so amazing. But obviously, there's many species on the planet, and our relationship, Homo sapiens' relationship with the rest of life, is just increasingly depleting natural stocks or changing what's going on. And so there's significant threats to natural biodiversity or straight up extinction induced by human beings. We'll have more to say about that in a minute. One of the places you can learn about this is an organization. When I started out bioengineering, I didn't know about this organization. It had been around. I just never heard about it because as a bioengineer, I only knew about people health and the National Institutes of Health and going to the doctor and trying to help medicine be better. But there's a whole other set of things going on related to planet health. And one of the groups that works on this quite a lot is called the IUCN, or the International Union for the Conservation of Nature. And if you go to their website, they maintain something called the Red List. The Red List is basically the endangered species list for not just the United States, but for Earth, right? And so I encourage you to go to this and take a look and like see which ones you like and what's going on with it. They represent that almost 40,000 species are threatened with extinction. And you can see how it's distributed. We haven't seen all the species. So there's more species threatened with extinction. These are just the ones we know about. The IUCN is a very interesting organization, it turns out. They're 70-some years old. They're based in Switzerland. They have 1,400 members, 1,400 members. But the members aren't people. The members are organizations. So they're an organization of organizations. So a nation could be a member of the IUCN, or a civil society organization, not-for-profit, could be a member of the IUCN. What's also very interesting is the IUCN maintains a permanent observer status with the United Nations in New York. So you think about like who's representing what country in the United Nations, and then suddenly the IUCN shows up and is like, we're representing nature, right? It's like such an interesting organization. I was able to travel to Switzerland, go east of Geneva on the train, and visit their headquarters in a town called Gland. And within their headquarters, you can see their library. And although their red list of endangered species is on the internet now, if you actually visit, the red list historically was kept track of on a card catalog, like those old library card catalog things. And I have to share with you how it felt when I pulled out the drawer and would start to thumb through the catalog of species and how the species were doing. And it had been typed out on a manual typewriter, species name found in this part of the world, and it's endangered, or then endangered got crossed out and somebody typed extinct. And it was such a profound heaviness because it forced me to understand that somebody who cared so much about these creatures, to make such a card catalog in the first place, because they love these creatures, and then to have to come back and type in all capital letters on the typewriter, extinct. It's just shockingly profound experience. Well, let's think about what's going on a little bit more systematically from an engineer's perspective, from a bioengineer's perspective. So here's a representation of the population of Homo sapiens on Earth. By the way, this slide, which I'm borrowing, from a corporation, says population of the Earth. We Homo sapiens love Homo sapiens so much that we don't even bother to say like population of humans on the Earth. It's just population of the Earth. So going back 300 years, and like the number of Homo sapiens is 2 billion around 1927, and then it's just clocking up. 3.5 billion in 1970 when I'm born. And so there's like over twice as many Homo sapiens as when I was born. That's interesting. On the left of this plot, I'm showing some examples of photographs from around Stanford. So the left one on the bottom is Redwood City Lumber Company, 1870, 1880 or thereabouts. There's a town very near Stanford, California called Redwood City. And it was given that name because that's where, once you cut down the redwood trees and turn that into lumber for construction, you'd ship it on boats, right, out into the San Francisco Bay to get to where it needed to be. Right, so that's why it's called Redwood City. We're cutting down redwood trees. The symbol, the animal on the California state flag is the California grizzly bear. That animal was last seen in the wild in California in 1924. Extinct in California in the wild. The engineering school at Stanford, where I work, we were started just the next year. We didn't go up Sand Hill Road to raise venture capital to start an internet company. You went up Sand Hill Road to go in the woods to cut down redwood trees, right? So like that's what engineering was about. In a way, that's what engineering is still about. It's like making things that insulate and protect people from the vagaries of nature. And ever since then, a lot more of us, right? Because engineering in that role has been very successful. But what's it doing to everything else? Well, everything that's not humans is having a different set of circumstances. All right, here's George the snail, the last of his species, dead at 14, now it's extinct. That was 2019. We see this is happening over and over and over again. So here's an article from colleagues at Stanford thinking about the environmental sciences. The title of this article reads, Accelerated Modern Human-Induced Species Losses, Entering the Sixth Mass Extinction. By sixth mass extinction, they're talking about through the entire history of life on Earth, there have been 5 previous times where most of life went extinct. And those were not caused by human beings, like the asteroid and the dinosaurs going extinct. Like that's one of the mass extinctions. But there's a sixth extinction, they argue. They write, since 1900 alone, 69 mammal species are believed to have gone extinct, along with about 400 other vertebrates. Evidence for species lost among other types of creatures is more difficult to come by, but we don't think it's doing better. And then why is this happening? Well, we're changing habitat, more land being used not for forest or jungle, but for farming. We're having invasive species show up that eat all the natural species. Industrialization and carbon emissions are changing the environment. Some of the things we're doing release toxins that don't just harm us, harm other things. Let's look at this a little bit more. So here's an example of a palm oil plantation. You can see in the middle of the slide, the biology looks very regular. These are oil palms, and they're used to make palm oil, which goes into food. Like if you have pancake mix from the supermarket, check out the ingredient list. You'll see palm oil. It's very useful for making nice pancakes. Also goes into many other consumer products. Well, to grow palm oil via oil palms, we got to get rid of everything else that's growing there, right? This forest or jungle. Now think about all the other things that live here, and when you get rid of that environment, how many of them are going to live in the oil palms? Not as many. That might be orangutans and other creatures. Right, so this is what we mean by changing land use, loss of habitat. What do we mean by invasive species? Here is a tree snake that used to not be on the island of Guam, and then through shipping and other sorts of human activities, suddenly it's there. And so it's going to eat the birds on Guam and other things that were native to Guam. If we think about carbon emissions and industrialization, that leads us to changes in the acidification of the ocean. That causes bleaching of coral systems. Right? Over 90% of the Great Barrier Reef in Australia is suffering from bleaching, says this story. More abstractly, we can quantify this. And remember, I was saying the human population doubled between 1970 and today, approximately. It's more than doubled now, 3.5 to 8 billion. Here's one index of natural biodiversity, all the other human things, and it's gone from a value, scaled value of 1 to about half. So stated differently, over my lifetime, the population of Homo sapiens has doubled, and the biodiversity of everything else has gone down by half. And there's definitely correlation, but from the preceding slides, we can see there's some causation as well. And wait, it's getting worse. For example, if you have a coronavirus pandemic that shuts down tourism, then maybe people who don't have other ways of earning a livelihood have to kill the things that the tourists would come, but there's no tourists coming because they're on lockdown. So let's just kill the endangered animals to get their rhino horns. Right. Let's just pause. What do you think? Should bioengineers care about natural biodiversity? Should bioengineers care about planet health? Well, hopefully you already have some examples. If we didn't have horseshoe crabs, we wouldn't be able to test for endotoxins without hurting rabbits. So it'd be good to keep the horseshoe crabs around, right? But is that the only reason? Are there other reasons? And I really want to encourage you to wrestle with this question. One of my answers is every natural creature, every lineage on Earth, every beautiful thing that predates us and exists, it's made of molecules. And molecules are gizmos. And maybe some of those gizmos are useful for bioengineering. Now that's a utility-based argument. I could give you a moral argument, but just like any bioengineer who actually wants to build with biology, who doesn't understand that each natural creature is a treasure trove, a library of useful molecules that who knows what they do. We know some of what they do, but they could do many more. It's like a Lego kit we haven't fully understood yet. Any bioengineer who wants to build with biology, well, you just have to be crazy not to want to keep things from going extinct, because it's where we're going to get all our gizmos. That's my utility argument. I'm very happy to make a moral argument, just like natural biodiversity is good, species are good in and of themselves. But let me give you an example of utility different from the limulus pyrogen test. This is a, quote, antifreeze protein. Now, they've been renamed. I think they're called ice structuring proteins now. But this is a protein isolated from the cold water ocean pout that is capable of modifying how water freezes. And what's very interesting about this protein is it allows these ocean pout creatures to exist in waters that are colder than freezing, like antifreeze. But it's not antifreeze that kills you, a poison. It's a protein-based antifreeze. It's an ice structuring protein. What's this good for? Ice cream. If you want to have really smooth ice cream, you got to use a lot of fat. You leave your ice cream in the freezer, and the freezer get freezer burn over time, right? As the freezer is modulating its temperature a little bit to keep frost from forming. And that freeze thawing, has these ice crystals growing. And so, the best way to avoid that historically is just have really fatty ice cream, right? Because that fat will keep the ice crystals from growing. That's good ice cream. But it's bad for you if you have heart disease or problems with cholesterol in your blood, perhaps. What if we could take, instead of adding more fat to the ice cream, just add in some of this fish protein by doing some bioengineering and making lots of that protein in a fermenter, purifying it, adding it to the ice cream. And now we have low-fat ice cream that doesn't grow ice crystals in your freezer. No freezer burn. All right, who knew? Better ice cream? You're welcome, says the ocean pout. Isn't that amazing? Every natural living creature is full of molecules, some of which we know what they do. And the more we know about what they do, the more we can use them to do other things that can be useful too. Again, I don't want to make the argument in favor of bioengineers caring for natural biodiversity only on the basis of utility. I think there's other ways of making this argument too. And so in general, let's think about how bioengineers make decisions, whether it's for biodiversity, biosafety, biosecurity. We'll get to those things later in the course. But generally, bioengineers are always confronting decisions whether this is the right thing to be doing or the wrong thing to be doing. And you're encountering that decision all the time in your life already. And underlying how you make these decisions is an idea, the moral compass, right? And so I'd encourage you to reflect a little bit about, how do I decide whether or not something's the right thing to do or the wrong thing to do? We weren't expecting to get that question in bioengineering, but of course it's here because biology matters so much. Anybody interacting with biology as an engineer is going to encounter these types of questions all the time. You need a moral compass, in other words, to be a good bioengineer. Let's look at some more examples of what's going on. This one I find incredible. This returns to the passing comment I made about snakes as an invasive species in Guam.
The brown tree snake has plagued Guam for years, destroying native wildlife, eating birds' eggs, biting residents, and knocking out electricity. Unlike many snakes, brown tree snakes eat prey they did not kill themselves and are vulnerable to acetaminophen. Taking advantage of these two weaknesses, scientists decided to airdrop dead mice laced with acetaminophen and attach them to streamers in areas near Guam's sprawling Andersen Air Force Base. The dead mice will be dropped by hand, one by one, from helicopters. Mice with streamers will be caught in the branches and the forest foliage where the snakes live and feed.
So I'm not sure if you caught all that. There's an invasive snake in Guam. It's preying on the natural species and the trees. And so we're going to try and get rid of this by having dead mouse paratroopers that have, I think, Tylenol tablets associated with them. So the snakes are going to eat the dead mice and then bleed out, basically, if I understand what's going on. And we've got this dead mouse with Tylenol tablets or acetaminophen taped to a streamer such that it gets caught in the branches so the snakes will eat it. What an incredible story. What an interesting way of trying to remove an invasive species. Is it going to work? It might help a little bit. I don't think it'll solve the problem completely. But hopefully it's like, could we do better? Do bioengineers have other tools we might imagine that could help with invasive species? Right? Here's another example. And this video can be a little bit disturbing. So take care. In this example,
house mice introduced.
We've got an invasive species, which is a mouse on islands where native birds are being born. Albatross, the big wingspan bird that glides long distances, soars long distances across the ocean. And the invasive mice are starving and hungry, so they're just going to eat the young albatross alive in the nest. Like, imagine being eaten alive by a mouse. Where did the mice come from? The mice weren't normally on the islands. They got there by swimming from another island, or more likely on a ship that landed or something like that. So how could we ever solve that problem? It turns out there's a very compelling organization, islandconservation.org, it's a charity. Entire mission is preventing extinction by removing invasive species from islands. And so I'd encourage you to think about, well, how could they go about this? How could you get mice that weren't normally on islands and are eating all the interesting reptiles and birds, eggs and young creatures, causing them to go extinct? How could you get rid of the rats and the mice that shouldn't be there? Well, you could use toxicants, put down poisons, like poisonous food, baited food, or you could put down lots of mouse traps, right? Rat traps, right? Or you could put down cats, something that a biological drug, something that eats mice and rats. Or maybe you could do some bioengineering. Maybe you could have a bioengineered mouse that if you introduce your bioengineered mouse onto the island, it would breed with the other mice and cause all the mice to go extinct. All right. So we've got options. And then I just want to jump down to this row here. Is the option socially acceptable? Is putting down poisoned food on an island socially acceptable? No, it's controversial. Why? Because something besides the mice might eat it and be hurt. What is putting down a bunch of rat traps controversial? Yep, it is. Because maybe it's painful to the rats, or maybe it doesn't work completely. What about adding cats? That's controversial because now we're just adding another invasive species to get rid of the first. How are we getting rid of the cats? We're going to add dogs. And how are we getting rid of the dogs? I don't know. What about bioengineering a mouse to breed with an invasive mice and cause the entire mouse population to go extinct? That'd be nice because I only have to get one of those mice. But what if that mouse gets off the island and then mice everywhere go extinct? That doesn't sound like a good idea. That's what's really interesting about the social acceptability role. Is every option is controversial. Oh, wait, there's one more option. Don't do anything. Just let all the native species go extinct. Well, of course, that's controversial because we don't want things to go extinct. At least I don't. So interesting. Every option is controversial. That's an opportunity. Could you make an option that wasn't controversial? Could you bioengineer something better? Which one, if you couldn't, would you choose of these? So just to zoom out and summarize, we've introduced the idea of planet health. We've framed some initial puzzles around, are there any things bioengineers could do related to changes in land use, related to things like species in places where they aren't historically found, related to climate change and its impact on the environment, coral bleaching, related to pollution. Should we ignore what's going on? Should we react? Should we change what we're doing to prevent some of these things from happening in the first place? Or is there something you can imagine still different to do? Hopefully at this point, when you stop to think about it, it's like, oh yeah, and there's a lot of bioengineering opportunity related to planet health. And note that we've only talked about biodiversity so far. There's other aspects of planet health too. Also think about this in the context of the future you wish for. What do you want to be true in the year 2030, 2040, 2050 regarding planet health? Remember, we were talking about Pixar starting to do things in the 1980s to get to Toy Story in the 1990s. That same type of thinking of being an anticipatory leader applies for planet health, along with tools and tool development and people health, all of bioengineering. So don't forget that part of what you're learning. Oh yeah, by the way, if we're too late, if something went extinct, could we bioengineer it back? Reflective questions, and then we're done. What's happening to life on Earth beyond Homo sapiens? What is biodiversity? How's it measured? How do we know what's going on? Who's keeping track? Should bioengineers care about any of this? Maybe we should just care about people. Like, we're working at the hospital and we're helping, and that's it, right? Or do you feel different? What are some of the most important bioengineering opportunities related to biodiversity and its conservation? What bioengineering knowledge and tools might help? Think of all the things you've learned so far, or the things you can imagine would be useful, but you haven't learned about yet.
Welcome to Introduction to Bioengineering.
All right. Another cool lecture.